I'm very, very grateful to Professor Vikash Sinha for his invitation. And of course, my association with Vikash goes back to many years, at least 2 decades. I've served in the faculty of this institute for 2 decades almost, and a large part of that was under the stewardship of Vikash as the institute director. I must say that although he and I worked on different things always, he of course was doing a lot of administration with great acumen, his inspiration and leadership was always there. And I think that's what makes a good director. So I think I had a great time here, despite all the ups and downs which you've heard about or read about. It was a great time to be at the Saha Institute under his leadership. I wish Vikash a very long life. Happy birthday on your 77th. What I'm going to talk about today is is about a piece of work we've done on compact binary mergers, and of course is motivated by the direct discovery of gravitational waves. So gravitational wave is basically ripples in space-time, whereby you have a passing gravitational pulse, say through this room. Then you have a momentary change in time duration and spatial distances when it's passing. And then, of course, things will come back to normal. And this was detected at LIGO. My previous speaker, Professor Bandyopadhyay, made a little allusion to that, but he, of course, referred to later detection. This is the earliest one. And there you see the 2 parts of LIGO at Hanford and Livingston, which were able to have come up with this detection, direct detection, this signal. And when you took the distance between them into account and superposed them, this is great. The way they match is so significant that you don't expect them to be anything but the same signal. But we still don't know where they came from. And that's part of the mystery. Are they a black hole merger? Do they constitute a phenomenon whereby 2 black holes come together, spin around each other, and then merge together in what you might think is a rather cataclysmic event and produce another black hole with a larger mass? We don't know that. LIGO data is consistent with BBH, with binary black hole merger, but there's no smoking gun. There is this alternative idea called boson stars, which are stars made out of Bose-Einstein condensates of very light bosons, but these are very heavy, almost the same, 30 solar masses or so. And it is possible that they merged. And if they merged, what did they merge into? So there are all these questions still hovering in people's minds. Now, of course, it depends on whom you talk to. There is a bias if you talk to the LIGO people, but there are others who give you a different picture. Now, the conundrum increased a little bit more with the Event Horizon discovery of 2019. And that's the discovery. Everybody has seen this picture. Now, it's funny that one of the journalists in an English newspaper came up with the idea that this observation is so beautiful. Look at the orange glow. Poor guy just didn't know that all this was of microwaves. This is the photon shadow. If you interpret it as NASA did in terms of a black hole, in terms of a black hole. So if you have a black hole in Messier 87, if you think there's a central black hole, a supermassive black hole, then that's the kind of picture which your simulation would give. On the other hand, if you simulated this with a boson star, you'd get a different picture. So obviously, the question is, how are they different? So that's the question. And what we don't know yet is which one is right. What is the real picture? So there's a question here. Now to tell you about the difference, what I'd like to say is that, well, I have to go a little bit back, especially if some of the younger people in the audience may not know. This is the space-time of special relativity. You have light cones, which are flat, which are absolutely like each other. So you have like shells going through each light cone. And If there was only special relativity in the universe, then one such light cone would describe all events, but you don't. And this is the great thing about general relativity. In general relativity, the light cones go all over the place. They not only tilt with respect to each other, but they also deform. And this is what Professor Penrose described the other day by comparing it with magnification and aberration. And distortion occurs because in gravity, in general relativity, there is something called the Weyl curvature. So there is a whole lot of difference. There's a complete non-uniform description of light cones. But at each light cone, the local measurement will give you the same value for the velocity of light, which will always travel along the edge of the cone. So local properties remain unchanged, which is why on Earth we are able to measure the velocity of light as we do. Now this, of course, is the picture that you've already seen in Penrose's talk, but this is an artist's rendition. An artist's rendition is often wrong, so here is a quiz for my student friends as to find where this picture is wrong. Basically, it gives you the evolution of a collapsing star, and here is what is called a trapped surface, which was described by Penrose also in his talk. And as you study the evolution, as you go along with time, the star begins to shrink beyond this region, which is the radius of the event horizon. That's the event horizon. The red marks here continues to shrink and shrink till it becomes a singularity. And of course, the local light cones inside get heavily distorted as one approaches the singularity. So that's the picture that we are familiar with. And this is the picture of a star. The space-time around the star has the same sort of tilting, but there is no trapped surface and there is no singularity. So these two are very basic differences. What we have to ascertain then is whether we're actually observing any information about the horizon. Now, before I go into what we did, I'd like to make a statement which I got from today's newspaper. I was astounded this morning that, in fact, while we have this picture from Event Horizon Telescope of Messier 87, the question was, why isn't there a similar picture for our local friendly neighborhood black hole sitting at the center of Milky Way? And the answer is there is now. Yesterday, there was an announcement that Sagittarius A star, which is our friendly neighborhood black hole, has now been mapped. You can see the photon shadow corresponding to that. The reason that we didn't see it before, because this black hole, for some reason, does not accrete too much. So the number of photons which will come from the accretion disk towards you gets smaller and smaller, and now they've accumulated sufficient amount of data. So if you check the newspaper, this is something that I'm overjoyed with. I would like to go back and look at the data itself. So what is it that we would like to do? We are unable to resolve between what caused the gravitational wave signal for GW150914. Is there a possibility that the boson star will evolve into a black hole? Such a proposal was made in 2020. Depends on certain assumptions about the accretion rate. Doesn't quite seem right. So we don't know when we will have sufficient data to resolve with some sufficient accuracy between a black hole and a possible binary exotic compact object. Our aim has been quite the opposite. Instead of trying to distinguish between the two things, which I think, or we think, is driven by data, so we have to wait for better statistics, we decided to see if you could make a prediction which is independent of the astrophysical character of the binary coalescence. And it turns out that if you use Bekenstein's limiting laws, you can actually provide a prediction. Even if the merger that LIGO saw isn't a black hole merger, what we were able to derive is a lower bound on the cross-sectional area of the post-merger element. And this is without any assumption about the astrophysical character. So this would be a check, because now we have lots and lots of binary coalescences observed by LIGO, Virgo, Khagra, and whatnot. I don't know if Khagra has actually made an observation, but they probably will soon. And there are other, as Devadesh Mandavada pointed out, there are other telescopes like LISA, which would be a space telescope, which will throw up more data on binary coalescence of compact stars. So it is likely that we will have a good way to check our prediction. This will be a prediction where loop quantum gravity makes a slight role. It's a very slight role, and I'll come back to that. And there are also possibilities of constraining neutron star masses, which Devadesh spoke about. So, do I have 15 minutes? How much time do I have? 15. Yeah. Okay, so let's begin with a little beginning because of student friends in the audience, laws of black hole mechanics, because there is a confusion about this. The laws of black hole mechanics are derived from classical gravity of black holes, which are solutions of the Einstein equation. And the first law, historically, was a discovery by Hawking that if you have two black holes coalescing, then they can certainly coalesce to a larger black hole, but the opposite process of a black hole decomposing into two light black holes is ruled out. So that's a consequence that the horizon area of a black hole will never decrease in any process. A further extension is that the surface gravity, which is something like the acceleration due to gravity at the horizon, is a constant. Now, there's no reason why it should be, because this is like everything in general relativity. It changes at every point in space and time. So why this should be a constant is a non-trivial law to derive from the Einstein equation. Finally, we have something that looks very close to the first law of thermodynamics, but it's completely a law in black hole mechanics, which says that if there's a change in the mass of a black hole, then of course there'll be a change in the surface gravity times the change, there'll be the change in the horizon area times the surface gravity at the horizon, plus terms which look like PDV and so on. And hence the idea that people associated a long time ago that perhaps entropy would be a key question because of the similarity, the visual similarity of this equation, which was derived from GR, with what we know from thermodynamics.
So you have 15 more minutes.
Thank you. Very good. So, how do we get from black hole mechanics to black hole thermodynamics? This was the work of Jakob Bekenstein. What he showed, what he argued is very simple, that if you have stuff like that, so this is accretion of a little black hole here from a blue giant star. So material is coming and forming an accretion disk and enters the horizon somewhere inside, and then of course there are jets coming out outside the event horizon. The jets always come out from outside the event horizon. Nothing ever comes out from the event horizon. So this is an accretion. An accreting black hole will of course mean that there is a decrease in the entropy outside. Of course, that just means that if that is the case, you have a violation of the second law of thermodynamics unless you attribute entropy to the black hole itself. And this is what he did. To agree with Hawking's theorem, he said this black hole entropy, he postulated must be proportional to area of the horizon. And then, of course, this is a statement of the generalized second law. The total entropy, which is the sum of the external entropy and the black hole entropy, can never decrease. So even if you throw me into a black hole, my entropy, as you see, is gone. That black hole will now have a slightly larger area and therefore slightly larger entropy. The question then that arises is, what are the microstates? This is a very big question, and there is a debate on this issue. What forms this entropy? And Bekenstein pointed out in the 70s itself that the origin of black hole entropy must be quantum gravity, must be states within the formulation of quantum gravity. So now, what I shall do is follow up on Bekenstein's idea, but fast forward back to the 2000s and talk about the formulation of quantum gravity in a very brief way called loop quantum gravity. Now, in this case, what you have is a background independent canonical quantization of general relativity. So you can call it quantum general relativity if you want. And we do there's some technical points about gauge fixing, we fix a gauge and so on. So we freeze one of the gauge invariances of general relativity, namely local boosts. You see, local Lorentz invariance is part of the gauge invariance of generativity, and we gauge fix them. Once this is done, things get much simpler because what you're left with is simply a rotational invariance SU2, and the conserved quantum numbers are spins, as you know. So the spins that we talk about come from the local Lorentz invariance of general relativity. They're not spins of particles. Well, this is, so I've again short-circuited the work by focusing on a picture of what quantum space would look like. So this is quantum space because we haven't been able to treat the full picture in a covariant way. So this is canonical, mind you, and when you do canonical physics, you're always on a time slice, on a spatial hypersurface. So on a spatial hypersurface, the space would look like a network. This network has two features, well, three features really. It has holes. Any network does have holes. These holes are typically of the size of Planck's scale, which is 10 to the minus 33 centimeters. Then the network is made up of edges, which is colors. These colors are supposed to signify spin. Spin goes from half, 1, 3 halves, and so on. And then you also have these vertices where these edges meet, and they're called intertwiners, and they are very easy. They're just Kronecker delta and the Levi-Civita symbol for SU2. So this is like a floating lattice. Floating because we have to remember Einstein, namely all frames are acceptable, known as diffeomorphism invariance. So this kind of a picture guarantees that you have diffeomorphism invariance. This is very different from the standard QCD lattice with which many of you may be familiar, which is a fixed lattice in space-time. This is a floating lattice. Now a few words about the horizon. It's a light-like surface. The horizon is light-like inner boundary of the outside space-time. It's a horizon because you don't know what's going on inside. And what it means is that the space-time distance on this light path is always going to be zero. Now, if you were to describe the states of the horizon, then the horizon becomes your universe, and you want to now describe a field theory, perhaps, you realize immediately that if you have a space-time with a degenerate metric, namely a light-like space-time, then you cannot have a standard Maxwell theory. So you can't have a standard Maxwell theory living on a black hole horizon. So what do we do? Well, there's a way out. If you take the degrees of freedom from the picture I showed you, so if you take the degrees of freedom as a projection of the loop quantum gravity degrees of freedom, which are connection degrees of freedom, having frozen the gauge fixed gauge to SU2, then you find that what you get is a Chern-Simons theory, which is a very weird kind of theory because it says that the field strength is proportional to the source. Now this is very different from the Maxwell's equations, right? Everybody will know that. So this is a new kind of theory. It's called a topological field theory, but this is the theory which allows us to estimate black hole entropy. This is what a quantum black hole would look like. So you go back to this picture and put in a sphere. And of course, what the edges will do will be to pierce the sphere and leave little conical singularities. So if you take enough of the conical singularities, you might just throw out the sphere and think of the conical singularities as a quantum description of the black hole horizon. When you do that, this is the one. You find these conical singularities different for different colors, different spins. They have all these conical singularities, but given the conical singularities, given they are like point charges interacting with the Chern-Simons fields which are moving around on the horizon. So you have a field theory problem. Now you have to solve that problem. What is the number of degrees of freedom corresponding to all these little functions? So you have Chern-Simons coupled to point charges. That's a problem which can be solved. And the answer that you get for a very large number of functions, I'll just come here, is this. Is that the black hole entropy is not only the one area law, which was postulated by Jakob Bekenstein and Stephen Hawking, but it's a whole slew of corrections. And the leading correction is a law. Okay, this was found by us about 50 years ago. And this is the Bekenstein-Hawking area. Now I come to the entropy bound, right? Do I have 7, 8 minutes? Yes. Yeah, okay, great. So the entropy bound, the statement. Because I'm short of time, I'll just go to this statement here. So if you take compact astrophysical objects, which will start with neutron stars, or include, of course, white dwarfs, black holes, and even some exotic compact objects like boson stars, gravitars, or gravastars, wormholes, and what have you, all of them, for a given cross-sectional area, will have an entropy which is less than a black hole entropy. Okay? So this is the impact of entropy bound, and the way to see this is to think of a sort of a virtual adiabatic accretion where the area doesn't change, but the entropy rises. But the maximum rise of the entropy of any compact object under accretion would be that of a black hole. So the black hole carries the maximum entropy for any compact star that you can imagine with the same cross-sectional area. So that means that therefore the entropy of any compact object which is not a black hole will be less than the black hole of the same horizon size, equal to the cross-sectional area. Okay? Now this is not a proof, it's kind of a motivation, but this does not require any special rate of accretion. So actual rate of accretion is irrelevant because we're doing a thought experiment which is a real virtual accretion. So we apply this in this case, so the compact object will have a less entropy than the black hole, the same horizon, of the horizon size, which is the same as the area. And then this is the second law. The second law will tell you that if it's a black hole merger, then the black hole horizon, the black hole entropy plus the gravitational wave entropy would certainly exceed the entropy of the two merging black holes. So you have a kind of thing like this. And here, I'd like to say that when we have this, we of course include these corrections. We call them holographic corrections because of the way they're calculated, it's really strange. I wish I could go into it. Maybe there's a question, I'll come back to this question of holography. It's in my title, so I'm entitled. I'm forced to mention a little bit about it. But basically, it's the way you compute this entropy. It's an entropy of a four-dimensional black hole, but you have to do a two-dimensional calculation to actually be able to calculate it. It's rather nice. So the question is, so these are systematically included. The question is, what if this was not a black hole? What if this was the merged remnant was not a black hole? Does it still hold? The answer is yes. And the way to see that is this is your consequence of the generalized black hole, generalized second law. The generalized second law gives you this, and the entropy bound itself gives you this. So if you put that in here, you get this formula. Now this is a sufficiency condition, but then if you want this formula to also hold for black hole binary mergers, it will also be a necessary requirement. So basically, it's the inequalities you play with which are derived from the two Bekenstein laws, the generalized second law of black hole of thermodynamics, including black holes, and the Bekenstein bound, which says that black holes have the largest area for any compact object with the same cross-sectional size. Good. So now we have the result in a rather compact, rather nice looking form, and we can try to see